Hi guys, you are welcome once again to the Smart Way lectures on the Science Ambassador series. This is a series of lectures we are bringing to you on all the areas in science. And today we are here with you to continue on chemistry. In our third video, we were able to solve for this question. We were able to explain by diagram what it means. Today we are going to take this question and analyze it so that we can understand the concept thermochemistry. So let's begin our journey. Here it is 25 cm cube of 2 molar HCl was added. This volume of this concentration 2 molar acid was added to 25 cm cube of 2 molar sodium hydroxide in an insulated beaker. That is, this is to prevent any heat loss, okay, just to make sure that all heats are maintained in the system after the acid come into contact with the base. The initial temperature of both solution was this, that is, at the start they were all this. The reaction mixture was stirred when it came together, and to ensure mixing, and the highest temperature reached for the solution was 33. Now calculate the heat change. This is also the same, so we are going to we are going to solve this question. Okay, we are going to solve this question. Now, to solve that question, we have to really understand what it means by that, okay? It means that we have an insulated beaker here. We have an insulated beaker, okay? And inside this beaker, you had either the acid or base initially inside. So the acid or base was inside. Let me change the color. So inside this beaker, we had the acid inside, and the thermometer was also inside. This was an insulated thermometer, was also inside, just to take the readings, okay, just to take the change in temperature. And then the initial temperature was what? Was 20 degrees Celsius, okay, and this was an acid. This was an acid. It was inside, and this is a thermometer, just to make sure that if there's any rise in this thermometer. And the base was added, so the base was added and mixed. So here a base was added and mixed, okay, so you add the base and mix. So when they added the base and mix and stirred it, okay, the temperature rose. So this was T1, okay. Here the temperature rose to what? To a new temperature, that is 33 degrees Celsius, 3 degrees, okay, that is a new temperature, that is T2. So originally both the acid, okay, in a different container, and the base also in a different container was initially as what? 20 degrees Celsius. But when they were brought together and stirred, the temperature rose from 20 to what? To 33. So this is it. And what happened? They were being asked to find the heat change, and they gave the specific capacity of the water. So here, what are you going to do? Always the data, put the data down. So quickly, let's write the given information. So here we're giving volume. We're giving volume. So volume of the acid HCl. The volume of the acid is equal to 25 cm cube. Okay. Then we are also giving the concentration. We're also giving concentration. or giving concentration of the acid to be equal to 2 molar. And we're also giving the volume of the base. That is sodium hydroxide. So here the volume of the base is 25 of the 2 molar sodium hydroxide. So it's 25. It's 25 cm3. Now, and we also have the concentration of the this is this. Concentration of sodium hydroxide is 2 what? Molar. So, and the specific capacity, that is the initial temperature, the T1 is equal to 20 degrees Celsius, and then the final temperature T2, when it was set, okay, and the mixture was brought, it was set, it was 33 degrees Celsius. And then the specific capacity of the water, the specific capacity of the water was given to us to be 4.8 kilojoules per kilogram per Kelvin. Okay, so this is the parameter. So quickly, what do we know? We know that when you bring acid into contact with a base, it's going to liberate energy. It's going to liberate heat. It's going to give out heat. Okay, it's going to give out what? Heat. Okay, so, and the solution, the two of them will mix to form what we call a salt solution. Will form what we call a salt solution. So, okay, and that process is called the neutralization reaction. Anytime you bring an acid and base together, it gives out heat. Energy, okay, comes out from the reaction. So you see, energy comes out from the reaction, and this energy, okay, the temperature takes the record of the energy. Okay, that is why when it was originally not, okay, mixed together, it was 20-20 from both sides. Both acid and base was 20, but when it was brought together, some amount of energy came out from the reaction. Okay, so it came out from the reaction, and the temperature recorded it from 20 to 23 degrees Celsius. So we are going to find for the heat that came out when the two was brought, and know that the heat that came out from the reaction, the heat that was produced from the reaction, have you gotten that? Now we'll go into the what to form the what, the salt solution, and we'll go into to form the salt solution, or will be taken by the salt. So the heat will leave the two acid and base and will now be in the salt solution. Remember, after it has been brought, there is no acid and there's no base again. It is only the salt solution that stays inside. And so the heat that, okay, the salt and the what, the heat that the acid and the what, the base produce will all go into the what, the salt solution. So once you know the salt solution, you know the mass and whatever of the salt solution, you can find for the heat given that will go into the salt solution. So to find for good. So to find for the heat change, all what you have to do is that the heat given out the heat what given out the heat given out by the acid and the base the heat given out by these two reactants will be equal to the heat what taken, equal to the heat taken or absorbed by the source solution, by the source solution. Okay, so by the source solution, so the heat given out by when the acid and the base came together will be taken by the source solution. So once we know the information about the salt, then we can know the heat that went from the solution. And so what do we know? We only know the specific capacity of the of the water. Here, what we are going to do is that we are going to do a little assumption here. Have you gotten that? So here they didn't give us anything of the salt. So what we are going to do is that usually the salt comprises of large amount of water. Okay, the salt comprises of the salt solution. The salt solution here comprises of large amount of water, and so we can say that we can assume that okay, the salt solution, okay, we can assume that the salt solution, okay, is the water. In this case, we can assume, this is an assumption, okay, is the water, because in this case what happened when the acid and base came together, they form what called a salt solution, but the water will be much more than the salt, and so we can use the water information to find for the heat. So we can assume that, okay, the heat that went into the salt solution is the same as the heat that went just into the water. Okay, so we can assume that, because what I said already, that usually large amount of water is formed, okay, together with the salt, but the water is large as compared to the salt. So we can say that the specific capacity, okay, the specific capacity of the of the salt solution, okay, we can regard it to be the same as that of the water, and then we can use the information of the water to find for the heat that came out from the salt solution, from the reaction between the acid and base. So since we know that the heat is calculated using the specific capacity times the mass where the heat went into and times the change in temperature, then we can simply get that. Okay, we can simply get that. So quickly, what are we going to do? We are going to say that, okay, the heat taken by the heat taken by the salt solution, which we are now saying that is the same as the water. The heat taken by the salt solution or the water. Remember, we assume that the salt solution is now the water. It's equal to the specific capacity of the water. If the salt solution was given, we use the salt solution. But because the specific capacity of the salt solution is not given, we assume that the salt solution is now water. So quickly, we do that. So we are going to get this is equal to the mass of the water times the specific capacity times the change in temperature. So both the acid and the base is made up of large amount of water. So we are going to get that. So once we do that, then we know the specific capacity of water. We know the mass of water. We can calculate for the mass of water. To calculate for the mass of water, they didn't give us the mass of water for many questions. They just gave us the volume of the acid, the volume of the base. They didn't give us the mass of water. But we can also calculate for the mass of water. Now usually the acid solution, okay, the acid solution, usually the volume of the acid solution is largely made up of water. Have you gotten that? The volume of the acid solution is largely made up of water. So the volume of So volume of acid solution, okay, and the base, okay, the volume of the acid solution and the base, okay, can be seen to be proportional to the volume of water, because in the acid and the acid solution and the base solution, most of the volume is water. It's just a small amount of acid that is inside. So we can also regard the volume of the acid to be the volume of the water, and the volume of the base to be what? The volume of also the water. Okay, we can also make that assumption. So it means that we know that the volume of water, we know the volume of what? Of water from the volume of acid and base. So the volume of water, okay, will be 25, okay, will be 25 cm3. Now plus another 25 cm3, okay, because both the acid and base contain large amount of water, and we are saying that the volume of acid should be equal to the volume of water. So we are going to get a total volume of almost about 500 watt 50 watt cm3 of water. Have you got that? Why are we calculating for the volume of water? Because we want to know the mass of the water. And how do we find for the mass of water? The mass of water is proportional to the density of water times what? The volume of the water. So quickly, because we know that the density is 1 gram per centimeter cube, then it means that the mass and the density are the same. Okay, so this is 1 gram per centimeter cube. This 1 gram per centimeter cube. This is what? Times 50 centimeter cube. So we can say that the mass of the water, the mass of the total water in the system is proportional to what? 50. We can say that the mass of the whole water, okay, we can say that the mass of the water, have you gotten that? Is proportional to 50 grams. Have you gotten that? So now that we know the water, okay, now that we know the mass of the what? Of the water, and also we know the temperature change, by subtracting this from this, we can just multiply and then we get our way through. So quickly let's move here and find for the heat change. Okay, so the heat change, which is proportional to the heat taken by the water. So the heat taken by the water is the question they are looking for as the heat change. Have you gotten that? It's proportional, so you just multiply the figures. We have 4.18 kilo, that is kilogram, that is Kelvin, that is kilo per watt per joule per kilogram per Kelvin, and then you multiply it times the what? You multiply it times the mass of the water, which we have calculated for. That is 50 watt grams, and 50 grams is the same as 0.0 kilogram, because we are doing our what calculation in standard units. This is in kilogram. The unit, this one is in kilogram. So we are doing our calculation in standard. So we are going to use 0.05 kilogram. And then we also multiply times the change in temperature. Between what? The change in temperature is from 33, that is 33 minus what? 20. Minus 20. Okay, so when you do your calculation, the change in what? The heat taken by the water, which is proportional to the heat change or evolve, is equal to 2.717 kilojoule. That is kilojoule. Why is it kilojoules? Because the unit will cancel. Okay, this is in what? Kelvin. This temperature is in Kelvin. Though it's in it is in Celsius before we subtracted. When you add 273 plus 273 and you do the subtraction, you are still going to get the same. That is why I still maintain this. So you can convert this one to 273 you can convert this one to Kelvin by adding this one plus 273 here plus 273, and then before you minus, you still going to get 13, of course. So you can't use this straightforward. And this is in Kelvin, that is in what? This in Kelvin, and there's also 1 Kelvin here. There's Kelvin per Kelvin here. There's Kelvin here. There's per Kelvin here. There's kilogram here, and there's also per kilogram here. So that will cancel to give kilojoule. So this is the final what? This is the final what? Energy. This is the final energy. So that is the assumption. So this is we have made a lot of assumptions here, which is it will be very close to the answer. Even when you use the precise thing, we've made a lot of assumptions. What you have to understand is that a neutralization reaction, the volume of the acid can be said to be the volume of water, and the volume of the base can also be said to the volume of water, because large amount of it comprises large amount of water, and the acid itself, the solid acid, a solid base itself, is very small inside. And so, and after you add it to, you get a source solution. So you can also still make that assumption that the source solution can also be regarded as water. And so when we put all those assumptions now, we can then find for the heat that both the acid and then the base gave out, okay, into the water. And then when we know the parameters of the water, such as the specific capacity of the water times the mass of the water times the change in temperature of the water, then we can then multiply the 3, and then we get the final answer. So this is the answer, the solution to the second question, per the fact that we've made this assumption. So that is it. All you need to understand is to know that the heat, okay, given in the reaction is the same as the specific capacity of the water, the mass, and this. And if no other terms are given to you, water can be used as the amount of heat that is what taken, okay, and that assumption is also correct. But if they give you the specific solutions, they gave you the what, if assuming they gave you the specific capacity of the solution, the source solution, you use the source solution. And if they give you the mass of the source solution, you use the mass of the source solution, and then you multiply times the change in temperature. But because they didn't give you the specific capacity of the source solution that was formed from the neutralization reaction, and also the mass of the source solution, you can make the assumption that since the source solution is largely made up of water, we can find for the heat taken by the water to be assumed to be that, and then you can find for the heat change. So basically, this will end the lecture on our 4th video. In our 5th video, we will be delving into some terminologies associated with energy and energy changes. Thank you.